In this problem, we have a ring of charge. It carries total charge Q. It has radius A. It doesn't say, but we're going to assume that that charge Q is uniformly distributed along the length of the ring. Our question is, let's find the electric field at point P due to this ring. Point P is a distance x away from the center, and it's along the axis of the ring. So there's our goal. First thing we do is we identify a small piece of charge dq. So our ring is made up of a bunch of small charges. Let's call this one little charge dq. Our little charge makes a little bit of electric field at the origin. Let's see if we can draw that vector. So here's the distance between the charge and our point. It makes an electric field that looks like this. Electric field is a vector, so we'll label that as a vector. A small bit of charge makes a small bit of electric field dE. So let's see what we have here. We want to find the total electric field, which means we have to find all of the components. Let's ask if any of the components cancel. So if we were going to draw these components in, the x component is the part that points along the x-axis. That's this part. The y component, so there's dEx. The y component is the part that points along the y-axis. That would come down this way. There's dEy. And our z component is the part that's parallel to the z-axis. That would come out of the page at us this way. A little bit hard to draw in 3D, but I hope you get the idea. dEz. So our electric field points this way, a little bit down, a little bit right, a little bit out. So our components are right, down, and out. So next, let's ask, how are we going to find the total electric field? We know that our net electric field is Ex in the x direction plus Ey in the y direction plus Ez in the z direction. And each of our components of electric field will be the sum of the individual components. So Ex is the integral of dEx. Ey is the integral of dEy. And Ez is the integral of dEz. So to get the total of any one component, we have to add up all the contributions due to each bit of charge all the way around the ring. We can go through and do the math on all three of them, but let's ask, do they simplify if we think about the symmetry? If we have a little bit of charge here, the y component points down. If we look at the little bit of charge over on this side opposite this one, that would make an electric field that pointed this way. That would be a little bit up. Those y components would cancel. Same thing if you had a piece here and here. So for everywhere on this part of the ring, the top half of the ring, the y points down. Bottom half of the ring, the y points up. So the net y component is actually going to be 0. Your z component is in and out of the page. For this part of the ring right here, the z component of electric field would point towards us. For this part of the ring right here, the electric field would point away from us. So if we added all those up, all those z components would cancel. So those two guys are going to be 0 by the symmetry of the problem. If you work through this problem and you don't catch on to that symmetry, it's okay. When you write your components and you start to do your calculation, when you come to your final answer, your answer is going to be 0 as you get around the ring there. Okay, so next, to find our total electric field, those guys are 0, so we want to find the x component of the electric field. So Ex is going to be dEx. So dEx is the x component of this vector right here. To find the x component, we need an angle, so we can do sine or cosine. Let's look at the angle right here. Let's call this guy theta. We see that our x component is adjacent to our angle, so dEx is going to be dE times cosine theta. Now let's remember, what do we mean by dE? dE is the little bit of electric field made by this little bit of charge. The electric field made by a point charge is E equals kq over r squared. So the electric field made by this charge element dq is going to be k times dq over r squared. And then our x component is times cosine theta. So what we'll do in the next part is we'll figure out what is dq, what is r, what is cosine theta. We'll put that together and we'll start to do our integral and solve for our problem. So our Ex is the integral of dx, which is the integral of this and the integral of this. So in the next part we'll sort out what we're going to put in for all of these things and we'll find our answer.